It's me. I'm back, Algebra 2 students. I accidentally hit a control on the previous video. If I had the time to, I would edit it and splice the two videos together and make it look nice. Not enough time for that, so let's just return to where we were at. We are on page 296. So I want to do a few example problems from that. Let's look at number 6. Let's look at number 6, which says 3 square root of 2 minus 5 square root of 2. That's one example. Let's look at 8. The cube root of 5 plus 5. Cube root of 5 plus the square root of 5. I'm sorry. Let's look at, let's see. Let me see which one I want to do. Let's look at 11, which is the square root of 45 minus the square root of 12 plus the square root of 180. Okay. And let me see. Just for kicks, the number 15. The square root of negative 25 minus the square root of negative 49. I'll do a couple others, but we're going to start with these. Look at 6. My radical expressions are the same. So 3 minus 5 is going to give me negative 2 square root of 2. Just like adding variables. Here, even though the radicand, the stuff under the radical, is the same, your indices are different. Can't add apples and oranges. Not possible. Here, you're going to want to break these down like we've talked about before. 45 is 9 times 5. The root of 9 is 3. 3 roots of 5. This is where your powers table will come in handy. 12 is 4 times 3. Well, root of 4 is 2. 2 root of 3. 180 is a little bit more interesting, but it's not that bad. Let's try what will go into this. Okay, actually, we don't want to use 3. We want to find our perfect squares. We want to find our perfect squares. My eraser lags on this. Is okay. 9's a perfect square. 9 will go into 180. 2 times 9 is 18. Well, 20 itself is 4 times 5. So 9 times 4 times 5 is equal to 180. 4 times 9 is 36, so it's 36 times 5. 36 is perfect. So you get 6 root of 5 for that. Okay? Now, these guys are common terms. 3 plus 6 is 9. 9 root of 5. 2 root of 3. You stop there because the roots of 5 and the roots of 3 are unlike terms. So you stop there. Last, 15. When you have a negative, that means an imaginary number. The root of 25 is 5i. The root of negative 49 is 7i. 5 minus 7 is negative 2. Negative 2i. Let me do one more that has some imaginaries in it. You've got number 17, which is the root of negative 20 plus the root of negative 45. 20 is 4 times 5, and it's a negative 4. Negative 9 times 5. Negative 4 comes out, 2i. Negative 9 comes out, 3i. So 2i plus 3i is 5i, root of 5. That's your answer there. So that really covers sums and differences of radicals. Let's talk about products. Products and quotients are pretty much the same. The product of radicals is a radical of a product. In other words, if you got two things multiplied together under separate radicals, you can stick them under the same radical. So to give an example of that, if I had the root of 4 times the root of 9, that's the same thing as the root of 4 times 9, which is 36, and the root of 36 is 6. Well, the root of 4 is 2, and the root of 9 is 3, and 2 times 3 is 6. So that proves it would work exactly the same both ways. Similarly, the root, the root of a quotient is the quotient of roots. So the square root of 16 over 25 would just be 4 over 5, or 0.8 if you insist on making it a decimal. Okay. So let's look at page 302. And let's do a couple examples. Number 1, root 8 times root 7. Number 2, 3 root 5 times root 6. 4 is interesting. Cube root of 7 times cube root of 49. And then let's look at 8, which is the square root of 2 times quantity, 1 plus the square root of 2. Okay, let's keep with those right now. Well, there's a couple of different ways you could do this. You could say 8 times 7 is 56. And then you would say what perfect root, what perfect square goes into that The answer is 4. So you would have 4 times 16, which is what, 50, 4 times, I'm sorry. 4 times 14 is 56. The 4 comes out 2 root of 14. That would be one way you could work it. The other way, you could simplify the 8 in the first place and have 2 square roots of 2, because 8 equals 4 times 2, and the 4 comes out. And then you would have times the root of 7, and that would directly get you there. 2 times 7 is 14, and your 2 stays outside. So 6 of one, half dozen the other. It works the same way both ways. Number 2, 3 is not going anywhere. 5 times 6 is 30. Boom, square root of 30, 3 square roots of 30. And that cannot be made any simpler because there is no perfect square that goes into 30. 4 is kind of sneaky. You get the cube root of 7 times 49. But what you might do is you might say, well, duh, 49 is actually 7 squared. 7 times 7 squared is actually the cube root of 7 cubed. The cube root of a cube cancels out, just 7. This is easy. Distributive property. Square root of 2 times 1 is the square root of 2. And the square root of 2 times itself cancels out, is just 2. Easy peasy. Now, if you have something like this, if you had the square root of 5 plus 2, these two different expressions are said to be conjugates, because when you multiply them, you lose the roots altogether. Watch what happens. If I said 5, the root of 5 plus 2 times the root of 5 minus 2, this is a FOIL problem. First, root of 5 times itself is 5. A square of a square root cancels out. First, outer, negative 2 root 5. Inner, positive 2 root 5. Last, 2 times negative 2 is negative 4. Well, look, these middle terms are the same, just different signs. Kabam, they cancel. So 5 minus 4 is 1, which is what that whole thing was equal to. So as I said, when you multiply conjugates, you lose the radical altogether. So on this same page that we are on, page 302, look at, for example, let me do an easy one, and then let me do a harder one. Let's look at 9. 9 is 5 times minus root of 2, 5 plus root of 2. And this is in a different order than the one I wrote earlier, same principle. First, 5 times 5 is 25. Well, I'm going to skip the outer and the inner. The outer is going to be 5 times the root of 2. The inner is going to be negative 5 root of 2. Those are going to cancel out. All I'm worried about is this times this. The root of 2 times itself is 2, and it's going to be negative. That's your answer. Let's skip down to 35, which looks like a horror, but it's not. The root of x plus 1 plus the root of x times the conjugate, in other words, the root of x plus 1 minus the root of x. Look at this and think, good heavens, how do I possibly do this? Easily. With a conjugate situation, the first two, you just get x plus 1. Simple as that. When you multiply a root by itself, the radical comes off. It cancels out. The two middle terms are gone, just like in the example I showed you on the previous screen. Root of x times minus root of x is just negative x. Well, the x's cancel. The answer of all that jazz is just 1. Okay. Let's look at division. Let's look at page 307. They're doing there. Page 307. Let's look at a couple there. Let's look at number 1, 2 over the root of 5. Let's look at number 2, the root of 1/5. Let's look at number 5, 48 over the root of 6. And let's look at 13, which is 2 cube root of 8 over the cube root of 2. Okay. The basic situation with a problem like 1, for historical reasons, back before they had calculators, the idea was you never ever wanted to have a radical on the bottom. Because, for example, the square root of 5, as I'm sure you all know, is approximately 2.236. And 2 divided by 2.236, which is what that would mean, is not a long division problem you really want to do if you can avoid it. So, what we do is this. We say, if I were to multiply the root of 5 by itself, two radicals times each other, I'm going to clear. That would give me a 5 in the bottom. That would be wonderful. However, in order for that to work, I have to say the root of 5 over itself, because this expression is just 1. You multiply anything by 1, you get itself back, so that doesn't change it. So that gives me 2 root of 5. That is the answer. And see, if you think of this from the days before calculators, that's easy to do, because you would have 2/5 root of 5. 2/5 is 0.4. 0.4 times 2.23 would be far, far, far easier to do than saying 2 divided by 2.236. That's the logic. Number 2, the quotient of a fraction is a fraction. Let me rephrase that. The root of a quotient is the quotient of roots. You bust it up. Any root of 1 is 1. You don't want that in the bottom, so you do the same thing as you did up in number 1. Multiply it by root of 5 over itself, and that gives you the root of 5 over 5, which is your answer. You look at 13. Oh, wait, I'm sorry, 5. We've not done 5 yet. You say, well, let me actually write that differently. I'm going to multiply it by the root of 6 over itself. So you're going to get 48 times the root of 6. Root of 6 times itself is 6. Well, 6 goes into 48. 6 times 8 is 48. That's my final answer, 8 root of 6. Finally, 13 looks intimidating, but this, we're going to kind of go backwards. Over here, I took a fraction and broke it up into two separate radicals. Here, we're going to do the opposite. I notice these are both cube roots, so I just say the cube root of 8 over 2. Well, 8 divided by 2 is 4, so I get 2 times the cube root of 4. Nothing else necessary. Okay. I really want you to dig on these. These videos are my way of trying to fill the gap where I could do these before you on the board at Cal, and I can't do that right now under the current circumstances. But I know you all can rise to the occasion. I want to push you a little bit. I want you to really dig in this, work on it, do the stuff. And I'm always welcome. I'm always willing to do these videos. I hope these are helping. I think this is enough to cover it for right now. This hits all the basic things. And don't hesitate among yourselves to video conference. You know, if one of you asks somebody else for help, you can do that as well. I'm always available myself as well. And if you want to set up a video conference, I'm doing that for the pre-calculus and physics people. And all of you guys are also in physics. So if you have some Algebra 2 questions you want to bring to the table, then I'm certainly willing to do that. I hope this has been helpful. I look forward to seeing as many of you as possible in the video conference tomorrow morning at 9. And I will talk to you later. Goodbye.